Hello, in this video we will look at common concentration expressions. Okay, so by no means is this list going to be exhaustive, but these are the common types of concentration expressions that I can recall that we typically use on a daily basis in an intro or a general chemistry class. The big one that we'll start with is molarity, which has the symbol capital M. Molarity by definition is moles of solute per liter of solution, and we should start by reminding the viewer that concentration in general, so this video is all about concentration in general is going to be an sorry, no, it's not. It's going to be an intensive property. Which means it's independent of sample size. So if you take a concentration and you chop it up into pieces, each piece has the same concentration. That's what I mean by intensive. Okay, so this is molarity, moles of solute over liter of solution. I have a little calculation here set up that we can try. Okay, and it reads 23.5 gram of NaCl is dissolved in water to make a 0.683 liter of solution. A, what is the molarity? B, how many moles of NaCl are contained in 0.01 liter of the above NaCl solution? Okay, so let's have a go at these calculations. We're going to use dimensional analysis. Okay, so the first one, part A, we want molarity. So that's going to be mole of NaCl per liter of solution. So we're going to start off with mole of NaCl as our numerator. And I know by definition that 1 mole of any chemical is its weight in grams. So I add the sodium and the chlorine together and I get 58.45 gram of NaCl. So then I can write gram of NaCl up here and I can cancel the unit off. I know from the question I added 23.5 gram of NaCl. That was one input. And then the overall volume of the solution was 0.683 liter. So you can see the only unit that survives are numerator moles of NaCl and the denominator liter of solution. Multiply all the numerators, divide by all the denominators. We're good for 3 sig figs, so we have 0.588 as our sig fig, so let's add a couple of non-sig figs, 6.5, that's what the calculator says. Our first insignificant digit adds 1 to our last significant digit on this occasion. So we round to 0.589 moles of NaCl solution. So that's what we have as our answer to part A. Our answer to part B, so I'll make that a bit smaller. Oh, didn't want to make that happen though. There we go. So part B, how many moles of NaCl are contained in a given volume? Alright, so let's have a look. So we want as our answer mole of NaCl. So let's write down mole of NaCl. I know from my solution to part A, and I'm not going to use the rounded value. You never use the rounded value, always use the non-rounded value. So I've got 0.588 0.65, and I know that that many moles is equal to 1 liter of our solution. So I can put liter of solution up here and cancel the units. And my input now was 0.0100 liter of solution. We run this through, we get 5.8865, again, pre-rounded value by 10 to the negative 3. Post-rounding, we round it to 5.89 by 10 to the negative 3. So again, we round to 3 sig figs. Okay, so that is molarity. That's what it is. That's a typical calculation. And I would say that molarity is definitely the most commonly used way to express concentration, at least in a regular chemistry class. Okay, moving on, something a little bit more exotic, molality. Molality has a lowercase m as a symbol, and this is, let's make this a little bit larger for now. Molality is moles of solute over kilogram of solvent. It's still an intensive property, but notice the numerator is the same as molarity, but the denominator is different. Notice because the denominator is mass now, we typically use when change in temperature is occurring. So you typically will use molality when you have a temperature variance, because in the case of molarity, volume is temperature sensitive. So you use when delta T is 0. Okay, so you cannot have a temperature variance when you use molarity, because liters of volume in general is temperature sensitive. You would then use molality. Okay, let's look at a sample calculation. Let's do a sample calculation. Okay. All right, so we have a question. 45.7 gram of magnesium chloride is dissolved in 2.4 kilogram of water. A, what is the molality of the solution? And B, how many moles of magnesium chloride are contained in 1.76 kilogram of solvent? Okay, so first up is A. So we are to calculate the molality. So we need mole of MgCl2 divided by kilogram of water, because water is our solvent here. So let's write mole of MgCl2. And again, by definition, a mole of any chemical is its weight in grams. So magnesium chloride has a weight of 95.24 grams, just by adding up the atomic masses of its constituent elements. I know on this occasion I have 45.7 grams of magnesium chloride. So I've got my moles already, and I know this has been dissolved in 2.4 kilogram of solvent, which is my denominator. So if I process these numbers on a calculator, and I'm good to round to 3 sig figs eventually, a pre-rounded value of 0.199, and then the final 9 and 3 are insignificant digits, but that first 9 after the dashed line adds 1 to the digit before the dashed line, so rounding to 3 sig figs, I get 0.200 moles per kilogram, or molality. Okay, moving on to part B. How many moles of MgCl2 or magnesium chloride are contained in 1.76 kilograms of solvent? So I need gram of MgCl2, gram of MgCl2. No, I don't. It's how many moles. I'm sorry. I'm not reading my own question. Moles. Let's make a bit more room over here. So I need mol MgCl2. Okay. Again, using the pre-rounded values from part A, I know that there's 0.19993 moles of magnesium chloride in 1 kilogram of water solvent. There's my water solvent, and on this occasion I actually have 1.76 kilograms of water solvent. Pre-rounded value of 0.35187. The 8 adds a digit to the previous digit, which is 1, so a rounded value to 3 sig figs. And 3 sig figs, because my 1.76 value is 3 sig figs, is 0.352 moles of magnesium chloride. Okay, so again, the difference between molarity and molality, you use molality either if you're asked to, or you choose to use it if you have a temperature variance during your experiment. Let's move on to something a bit more exotic, but not that much. Osmolarity. So here we're going to use, instead of moles per liter, we're going to use osmoles per liter. So this is osmoles of solute per liter of solution. Okay. Now here the big difference is, what's the difference between an osmole and a mole? Here osmoles, because osmoles are a colligative property, we're interested in the number of species dissolved. Okay, in the solution. Okay, so we'll keep that in mind. All right, so here's our question. Let's see how much room we have. No, don't want it to do that. Okay, so here's our question. We've got plenty of room. Okay. So the question reads, 7.58 grams of C3H8O is added to water to make a 1.5 liter solution. A, how many osmoles are in 1 mole of this chemical when it dissolves? And B, what's the osmolarity of the chemical when it dissolves? Okay, so let's have a look at that. We're going to set up a dimensional analysis question. Okay, so I need osmoles. So osmoles. So I write osmoles. Now, because C3H8O is a covalent compound, it's a non-electrolyte. So it doesn't split up into ions, for example. So it's got a 1-to-1 osmole to mole ratio because it's just one object, one lump of material. So 1 osmole is the same in this case as 1 mole of C3H8O. In other words, 1 mole of this stuff doesn't split up into anything, so it's just 1 osmole. So mole C3H8O. By definition, a mole of this chemical, we add up the weight of all the ingredients, so 60.10 grams of C3H8O, gram of C3H8O. My input here is 7.58 gram of C3H8O, and that is in a solution which is 1.5 liter. Actually don't need, sorry, I was reading the wrong question on that occasion. So I just need to finish there. Alright, I'm quickly going to check this calculation just to make sure I haven't made a calculation mistake as we go live. 7.58 divided by 60.1.12. How many osmoles? Okay, I'm looking at this and I'm thinking, do I need the volume? How many osmoles are in it when it dissolves? Yeah, I do. I think I was right initially, and then I started to doubt it. I do, because I need to know. So I do, I believe, need the 1.50 liter of solution. So let's try and. I'm feeling more and more confident that that's what I need. So let's see why. The question reads, how many osmoles are in 1 mole when it dissolves? How many osmoles? Do you know what? I think maybe, having said all of that, and I apologize for doing this live, but I really don't want to lose the 17 minutes of video I've made. Because this can happen, you can do a calculation and then change your mind, that's okay. Scientists do it all the time. I think I've made this far more complicated than it really was the way I presented it. Okay, start again. How many osmoles are in 1 mole? Okay, so I need osmoles. Well, because it is 1 osmole is 1 mole of C3H8O. That's the equivalence, and I'm after 1 mole of C3H8O. Then the answer is 1. Done. Boom. Okay. So why are we saying, where does this come from? Why is it this 1-to-1 equivalence? This is because it's a non-electrolyte. It's a non-electrolyte, and recall that we're interested in number of dissolved species. So when a non-electrolyte dissolves, it just stays as one unseparated object. Okay. All right. So we finally got there. Sorry that took longer than anticipated, but best to catch an issue before we publish. Okay, B. Let me make a note to change that. Okay, part B reads, what is the osmolarity of the solution? Okay, so I need to figure out how many moles we have. Okay, so I need osmoles per liter of solution, osmoles. Okay, so this is where I need to say that 1 osmol is equal to 1 mole of C3H8O. C3H8O. I know that 1 mole is 60.1 gram of C3H8O. It's just the weight in grams. So gram C3H8O. On this occasion, I had 7.58 gram of C3H8O, and it was present in 1.50 liter of solution. Okay, so if we multiply all of that through, let's see what we get. So again, I've got to calculate this live. So 7.58 divided by 1.5 divided by 60.1. Okay, so we get, now we'd have to ultimately round this to 3 sig figs, so pre-rounded value of 0.084082, which gives us a rounded value of 0.0840. And on this occasion, I'm using the rule that says if, sorry, I beg your pardon, that should be a 1. 8 is larger than 5, so we add 1 to the previous digit. So rounded value of 0.0841. Okay. Okay, we got there. That was sluggish, but we got there. And then the next thing I want to look at is weight volume percent. There are variations of weight volume percent. You can have weight percent, volume percent, but if we do weight volume, you'll get the idea. And I think pretty consistently I'm going to have the wrong color pen when I go to write. This is going to be the mass or the weight typically in gram, of solute over the volume, typically in milliliter, of solution as a percentage. So same, it's an intensive property, just a different way to present the intensive property. Much more likely to be used in a biological allied health type situation. Okay, so here's a sample question, so let's have a go at this one. The question reads, a glucose solution is made from 5 grams of glucose dissolved in water to make 200 ml of a solution. A, what is the percent weight volume of the solution? B, what volume in milliliter of the solution would contain 0.0735 grams of glucose? Okay. So let's have a go at this one. Okay, so this first one, we're just going to use, you could squeeze it in dimensional analysis, but probably just good old algebra would probably be the most user-friendly in this case. So we clearly have 5 gram of solute. We know the solute is the smaller smaller quantity, and we have 200 ml of our solution as 100%. Well, that's going to be 2.5% to 3 sig figs. Now what that tells us, this tells us that 2.5 gram of glucose is equal to 100 ml of solution. So that's the equality that we learn from the percentage. Given 100 ml of that solution, we know that 2.50 grams is glucose. And that will help us in part B. When it says what volume, okay, so now we're going to return to more dimensional analysis. We're going to use our equality, so I ultimately need milliliter of solution. And I can use my equality now. I know that 100 ml of solution is equal to 2.5 gram of glucose. So I can write gram of glucose here. And my input is 0.0735 gram of glucose. So that would give me, let's see, that would give me 0.294 milliliter of solution. Okay, and again, you could have variations on the theme, but pretty much there's everything there that you need to be useful when doing weight volume and that type of calculation. Moving on to equivalence. Equivalence essentially looks at really depends what you're looking at in terms of equivalent. There's different types of equivalence, acid-base equivalence, redox equivalence, but ignoring that for now, just let's look at general equivalence. Equivalence essentially is looking at the number of charge, essentially the number of charges. Now, if you're looking at acid-base equivalence, it's, acid equivalence would be hydronium charges, base equivalence would be hydroxide charges. If you were looking at redox equivalence, it would be electronic charges. So again, it's a broad idea when you say the word equivalence. For now, I'm just going to talk about charges in general. Okay, now equivalence per se, I have to be careful here because I build this video as common expressions of concentration. Equivalence is not exactly a concentration, but it's used in a concentration, which we'll get to in the next page. So I have to preface this, I guess, by saying it's not a concentration, but it's used as a numerator in normality, which we'll see in the next page. And normality is a concentration. So this is a preview or a build-up to normality. Okay, so having said that, let's look at a question. Okay, so the first question, 234.5 gram of KCl is dissolved in water to make 3.6 liter of solution. How many equivalents of K plus potassium charges are in 1 mole of KCl? Okay, So this is the answer to A. So we've got, I want equivalence, number of charges per mole of KCl. Now specifically, it's equivalence of K in. So if it just said equivalence, we'd have to look at K and Cl, but the question specifically says K only. So keep that in mind. So equivalence of K, I know that there's one equivalent of K is equal to 1 mole of KCl. And that's a no-brainer. It's just because there's one K in KCl. Okay. So I've got mole of KCl here. By definition, a mole sorry, I didn't need to erase that, did I? I didn't need to obscure that. I just need to say I'm interested in 1 mole of KCl. All right. So again, if I try not to overinterpret the question, how many equivalents of K are in 1 mole of KCl? That's what I need. That's what threw me off. No. Okay, we'll get there. All right, 1 mole of KCl, 1 mole of KCl. So I just have a number of equivalents, and the answer is 1. Okay, very good. Very good. Okay, second question, part B. What is the concentration of K in equivalents per liter? Okay, so I need equivalence of K per liter of solution. Now this, folks, this is a concentration. This is normality. Capital N. So this is our preview, what we mentioned earlier, our preview. Equivalence itself is not a concentration, but normality is. We just had to involve a denominator. Okay. So equivalence per liter, that's normality. So I could have said what's the normality? Why don't I do that? What is the normality? Okay, so we know that there's one equivalent of K plus is equal to 1 mole of KCl. Mole of KCl. I know that 1 mole of KCl by definition is the sum of all its atomic constituents, which is 74.56 grams of KCl. Gram of KCl. I have 234.5 gram of KCl in this question. And my total volume of solution is 3.6 liter. Okay, so I run that through and I have a pre-rounded value of 0.8736, which rounds to 0.87 equivalents of K per liter, or 0.86 normal. Okay, so that's normality. Second normality question reads 0.25 gram of aluminum sulfate is dissolved in water to make 150 ml of solution. Let's put a decimal there to make that 3 sig figs, otherwise we'll have to round a crazy amount. How many equivalents of sulfate ion are in 1 mole of aluminum sulfate? And I added this question just so that you can see that it really is the amount of charge. So I gave something with more than one charge. Okay. So if we look at aluminum sulfate, sulfate is SO4 2-, but aluminum sulfate has 3 of those. So I've got 3 lots of SO4 2-, which means I have 6 charges. So that means I've got 6 equivalents of SO4 2- in 1 mole of Al2 SO4. And my input is 1 mole of Al2 SO4. So I've got 6. So it really is the number of charges, and I wanted to just emphasize that a little bit. Okay, and this is the last page in this video. We did talk about normality in the previous page, but we introduced it with equivalence. Now we're experts on equivalence. We can go right to normality itself from the get-go. And this is equivalence per liter of solution. That was supposed to be solution. It looks like John somehow. So solution. And again, you know, equivalence of what? In general, just number of charges, but it can be specific if you're looking at different types of chemistry. In acid-base chemistry, you would look at charges of important species. Acid equivalents would be hydronium ions. Base equivalents would be hydroxide ions. If you're looking at a salt in general, just look at charges in general. So it really depends on the specific type of chemistry you're in when you use the word normality. Okay, so let's have a look at this question. It reads, a 1 gram sample, a 1 gram sample of H2C2O4, 2H2O, so oxalic acid dihydrate, is titrated with 44.51 mil of sodium hydroxide. Calculate the normality of the sodium hydroxide solution. Okay, so let's use our dimensional analysis again. First thing we should probably do is come up with a balanced equation though, right? So we balance an equation, we've got it's a neutralization reaction, so the sodium hydroxide, I'm going to ignore, so I'm actually going to ignore that. Let's get rid of that because I don't want the dihydrate. So I've changed the question just because I don't want to have to worry about the water that's going to become part of the bulk anyway. So we'll just say it's oxalic acid with no extra water. Okay. H2C2O4, we're going to produce, put the 2 in the wrong place. We're going to produce water and salt. Okay, and now we can balance it with a 2 here to balance the sodium and a 2 here to counterbalance the extra hydrogens that we added. Okay, so now we have a balanced equation. We're in a position to quantify equivalence per liter, which is just normality. Okay, so now because I'm looking at NaOH, I know that it's the hydroxide that is the active equivalent, so I'm going to say 1 equivalent is equal to 1 mole of NaOH. So I want to be careful when I explain why. So NaOH is obviously Na plus and OH minus. Okay, but so you might argue that, okay, the equivalent should be 2, but we know that Na plus is a spectator ion in acid-base chemistry. So it really doesn't do anything. So we're going to look at this as the important, in fact, the only important charge. And because there's only one important charge in this acid-base chemistry, we'll go for one equivalent. So that's how you tailor it slightly depending on the situation. Okay, so mole of NaOH. From the balanced equation, I have 2 moles of NaOH, and that's equal to 1 mole of our oxalic acid. By definition, a mole of oxalic acid is its weight in grams, so that's 126.07 grams of oxalic acid. And on this occasion, I had a gram. So this is going to give me 0.01586 so what's that extra digit? Don't have the extra digit right in front of me. So let's see, 1 by 2 by 1 divided by 158,642. I give the extra digit. So then my rounded value would just be 0.01586 equivalents. Or I could say, so I divide that by 1,000, 1, 2, 3. I could say 15.86 milli equivalents per liter of solution. Or I could just say 15.86 millinormal. Okay, and that will conclude this video. Just to recap, this video was looking at not an exhaustive list, but common concentration expressions. We looked at molarity, we looked at molality, we looked at osmolarity. We didn't look at osmolality, but it doesn't take much of a leap to see that we just replace the denominator with kilogram of solution. We looked at weight volume percent. We looked at equivalence as a prelude to normality. We mentioned that normality can be specific, depending on the type of chemistry it's applied to. And we specifically looked at acid-base normality. Okay, and that will do us. Bye for now.